Habituation is a form of learning in which an organism decreases or ceases to respond to a stimulus after repeated presentations. Essentially, the organism learns to stop responding to a stimulus which is no longer biologically relevant. For example, organisms may habituate to repeated sudden loud noises when they learn these have no consequences. Habituation usually refers to a reduction in innate behaviours, rather than behaviours developed during conditioning, in which the process is termed extinction. A progressive decline of a behaviour in a habituation procedure may also reflect non-specific effects such as fatigue, which must be ruled out when the interest is in habituation as a learning process. The habituation process is a form of adaptive behaviour that is classified as non-associative learning. Non-associative learning is a change in a response to a stimulus that does not involve associating the presented stimulus with another stimulus or event such as a reward or punishment. Habituation is the decrease of a response to a repeated eliciting stimulus that is not due to sensory adaptation or motor fatigue. Sensory adaptation occurs when an organism can no longer detect the stimulus as efficiently as when first presented, and motor fatigue occurs when an organism is able to detect the stimulus but can no longer respond efficiently. In contrast, habituation is a learned adaptation to the repeated presentation of a stimulus, not a reduction in sensory or motor ability. Some related phenomena to habituation include sensitization and stimulus generalization. Discrimination. Sensitization is the opposite process to habituation, i.e., an increase in the elicited behavior from repeated presentation of a stimulus. There may also be an initial increase in response immediately prior to the decline. Another related phenomenon is stimulus generalization, when habituation occurs in response to other stimuli that are similar to the original stimulus. The opposing process, stimulus discrimination, is when habituation does not occur to other stimuli that are similar to the original stimulus. Drug habituation. There is an additional connotation to the term habituation which applies to psychological dependency on drugs, and is included in several online dictionaries. A team of specialists from the World Health Organization assembled in 1957 to address the problem of drug addiction and adopted the term drug habituation to distinguish some drug use behaviors from drug addiction. According to the WHO lexicon of alcohol and drug terms, habituation is defined as becoming accustomed to any behavior or condition, including psychoactive substance use. By 1964, the American Surgeon General Report on Smoking and Health included 4 features that characterize drug habituation according to WHO. 1. A desire to continue taking the drug for the sense of improved well-being which it engenders. 2. Little or no tendency to increase the dose. 3. Some degree of psychic dependence on the effect of the drug, but absence of physical dependence and hence of an abstinence syndrome. 4. Detrimental effects, if any, primarily on the individual. However, also in 1964, a committee from the World Health Organization once again convened and decided the definitions of drug habituation and drug addiction were insufficient, replacing the 2 terms with drug dependence. Substance dependence is the preferred term today when describing drug-related disorders, whereas the use of the term drug habituation has declined substantially. This is not to be confused with true habituation to drugs, wherein repeated doses have an increasingly diminished effect, as is often seen in addicts or persons taking painkillers frequently. characteristics. Habituation as a form of non-associative learning can be distinguished from other behavioral changes by considering the characteristics of habituation that have been identified over several decades of research. The characteristics first described by Thompson and Spencer have recently been updated and include the following. Repeated presentation of a stimulus will cause a decrease in reaction to the stimulus. Habituation is also proclaimed to be a form of implicit learning, which is commonly the case with continually repeated stimuli. This characteristic is consistent with the definition of habituation as a procedure, but to confirm habituation as a process, additional characteristics must be demonstrated. Also observed is spontaneous recovery. That is, a habituated response to a stimulus recovers when a significant amount of time passes between stimulus presentations. Potentiation of habituation is observed when tests of spontaneous recovery are given repeatedly. In this phenomenon, the decrease in responding that follows spontaneous recovery becomes more rapid with each test of spontaneous recovery. Also noted was that an increase in the frequency of stimulus presentation will increase the rate of habituation. Furthermore, continued exposure to the stimulus after the habituated response has plateaued may have additional effects on subsequent tests of behavior, such as delaying spontaneous recovery. The concepts of stimulus generalization and stimulus discrimination will be observed. Habituation to an original stimulus will also occur to other stimuli that are similar to the original stimulus. The more similar the new stimulus is to the original stimulus, the greater the habituation that will be observed. When a subject shows habituation to a new stimulus that is similar to the original stimulus but not to a stimulus that is different from the original stimulus, then the subject is showing stimulus discrimination. Stimulus discrimination can be used to rule out sensory adaptation and fatigue as an alternative explanation of the habituation process. Another observation mentioned is when a single introduction of a different stimulus late in the habituation procedure when responding to the eliciting stimulus has declined can cause an increase in the habituated response. This increase in responding is temporary and is called dishabituation, and always occurs to the original eliciting stimulus. Researchers also use evidence of dishabituation to rule out sensory adaptation and fatigue as alternative explanations of the habituation process. Habituation of dishabituation can occur. The amount of dishabituation that occurs as a result of the introduction of a different stimulus can decrease after repeated presentation of the dishabituating stimulus. Some habituation procedures appear to result in a habituation process that lasts days or weeks. This is considered long-term habituation. It persists over long durations of time. Long-term habituation can be distinguished from short-term habituation, which is identified by the 9 characteristics listed above. Biological mechanisms. Habituation can refer to a decrease in behavior, subjective experience, or synaptic transmission. The changes in synaptic transmission that occur during habituation have been well characterized in the aplysia-Gillen-siphon withdrawal reflex. Habituation has been shown in essentially every species of animal. The experimental investigation of simple organisms such as the large protozoan Stentocoeruleus provides an understanding of the cellular mechanisms that are involved in the habituation process. Neuroimaging. Within psychology, habituation has been studied through different forms of neuroimaging like PET scan and fMRI. Habituation is observed after repeated presentations of stimuli. Within fMRI. The stimulu's effect is measured using blood oxygen level dependent signals, where long-term decreases of the bold signal are interpreted as habituation and increases of the bold signal are considered sensitization. The amygdala is one of the most studied areas of the brain when looking at habituation. One of the most common ways to study this is to observe the visual processing of facial expressions. A study by Breiter and colleagues used fMRI scans to identify which areas of the brain habituate and at what rate this happens. The results of the study showed that the human amygdala responds and rapidly habituates preferentially to fearful facial expressions over neutral. They also observed significant amygdala signal changes in response to happy faces over neutral faces. One of the most recent studies that has looked at habituation was run by Blackford, Allen, Cowan, and Avery. In 2012 they looked at the effect extreme inhibited temperaments versus extreme uninhibited temperaments has on habituation. The study found that individuals with uninhibited temperament demonstrated habituation in both the amygdala and hippocampus regions of the brain, whereas participants with inhibited temperaments, these regions of the brain failed to habituate over repeated presentations. The researchers suggest that this failure to habituate reflects a social learning deficit in individuals with an extreme inhibited temperament, which may provide a possible mechanism for higher risk of social anxiety. History. Early studies relied on the demonstration of dishabituation to distinguish habituation from sensory adaptation and fatigue. More recently, stimulus specificity and frequency-dependent spontaneous recovery have been identified as experimental evidence for the habituation process. Sensitization is also conceptualized as a non-associative process because it involves an increase in responding with repeated presentations to a single stimulus. Much less is understood about sensitization than habituation, but the sensitization process is often observed along with the habituation process. Theories. In an article written 20 years after his initial research with Groves, renowned authority on the behavioral phenomenon of habituation, Richard F. Thompson, reviews several theories of the process of habituation. The stimulus model comparator theory formulated by Evgeny Sokolov and the Groves and Thompson dual process theory are two examples. The stimulus model comparator theory emerged from the research of Sokolov, who used the orienting response as the cornerstone of his studies, and operationally defining the orienting response as EEG activity. Orienting response is a heightened sensitivity experienced by an organism when exposed to a new or changing stimulus. Orienting responses can result in overt, observable behaviors as well as psychophysiological responses such as EEG activity and undergo habituation with repeated presentation of the eliciting stimulus. The Sokolov model assumes that when a stimulus is experienced several times, the nervous system creates a model of the expected stimulus. With additional presentations of the stimulus, the experienced stimulus is compared with the stimulus model. If the experienced stimulus matches the stimulus model, responding is inhibited. At first, the stimulus model is not a very good representation of the presented stimulus, and therefore there is a mismatch and responding continues. But with additional presentations, the stimulus model is improved. Consequently, there is no longer a mismatch and responding is inhibited, causing habituation. However, if the stimulus is changed so that it no longer matches the stimulus model, the inhibition of the orienting response is weakened, and an orienting response returns. Sokolov places the location of the stimulus model within the cerebral cortex of the brain. The Groves and Thompson dual process theory of habituation posits that two separate processes exist in the central nervous system that interacts to produce habituation. The two distinct processes are a habituation process and a sensitization process. The dual process theory argues that all noticeable stimuli will elicit both of these processes and that the behavioral output will reflect a summation of both processes. The habituation process is decremental, whereas the sensitization process is incremental, enhancing the tendency to respond. Thus, when the habituation process exceeds the sensitization process, behavior shows habituation. But if the sensitization process exceeds the habituation process, then behavior shows sensitization. Groves and Thompson hypothesized the existence of two neural pathways, an SR pathway involved with the habituation process, and a state pathway involved with sensitization. The state system is seen as equivalent to a general state of arousal. Examples of the habituation process in animals and humans. Habituation has been observed in an enormously wide range of species, from motile single-celled organisms such as the amoeba and Stenocoeruleus to sea slugs to humans. Habituation processes are adaptive, allowing animals to adjust their innate behaviors to changes in the natural world. A natural animal instinct, for example, is to protect themselves and their territory from any danger and potential predators. It is obvious that an animal needs to respond quickly to the sudden appearance of a predator. What may be less obvious is the importance of defensive responses to the sudden appearance of any new, unfamiliar stimulus, whether it is dangerous or not. An initial defensive response to a new stimulus is important because if an animal fails to respond to a potentially dangerous unknown stimulus, the results could be deadly. Despite this initial, innate defensive response to an unfamiliar stimulus, the response becomes habituated if the stimulus repeatedly occurs but causes no harm. An example of this is the prairie dog habituating to humans. Prairie dogs give alarm calls when they detect a potentially dangerous stimulus. This defensive call occurs when any mammal, snake, or large bird approaches them. However, they habituate to noises, such as human footsteps, that occur repeatedly but result in no harm to them. If prairie dogs never habituate to non-threatening stimuli, they would be constantly sending out alarm calls and wasting the time and energy. However, the habituation process in prairie dogs may depend on several factors, including the particular defensive response. In one study that measured several different responses to the repeated presence of humans, the alarm calls of prairie dogs showed habituation, whereas the behavior of escaping into the burrows showed sensitization. Another example of the importance of habituation in the animal world is provided by a study with harbor seals. In one study, researchers measured the responses of harbor seals to underwater calls of different types of killer whales. The seals showed a strong response when they heard the calls of mammal-eating killer whales. However, they did not respond strongly when hearing familiar calls of the local fish-eating population. The seals, therefore, are capable of habituating to the calls of harmless predators, in this case harmless killer whales. While some researchers prefer to simply describe the adaptive value of observable habituated behavior, others find it useful to infer psychological processes from the observed behavior change. For example, habituation of aggressive responses in male bullfrogs has been explained as an attentional learning process that allows animals to form enduring mental representations of the physical properties of a repeated stimulus and to shift the focus of attention away from sources of irrelevant or unimportant stimulation. Habituation of innate defensive behaviours is also adaptive in humans, such as habituation of a startle response to a sudden loud noise. But habituation is much more ubiquitous even in humans. An example of habituation that is an essential element of everyone's life is the changing response to food as it is repeatedly experienced during a meal. When people eat the same food during a meal, they begin to respond less to the food as they become habituated to the motivating properties of the food and decrease the consumption. Eating less during a meal is usually interpreted as reaching satiety or getting full. But experiments suggest that habituation also plays an important role. Many experiments with animals and humans have shown that providing variety in a meal increases the amount that is consumed in a meal, most likely because habituation is stimulus-specific and because variety may introduce dishabituation effects. Food variety also slows the rate of habituation in children and may be an important contributing factor to the recent increases in obesity. We also find that habituation is found in our emotional responses, called the opponent process theory, proposed by researchers Richard Solomon and John Corbett. It is known that responses by the subject tends to change by repetitively presenting certain stimuli. But concerning the opponent process theory, some emotional reactions to the stimuli weaken while others' reactions are strengthened. Take for example, that is the end of the semester at your university. You have been worried about your grade for the entire semester and you need to make an A on the final in order to pass the course. You study efficiently for the test and after taking it, you feel that you will receive a very high grade. But once you check the grade book, you see that you did not get an A on your exam. Instead you received a C+. Now you are distraught and know that there is no other way to pass the course for the semester. After a few minutes you begin to calm down and by the next hour you are back to your normal emotional state. This is an example of an emotional response explained by the opponent process theory. It begins with an outside stimulus provoking an emotional reaction that increases rapidly until it is at its most intense. Gradually, your emotional state declines to a level lower than normal and eventually returns to neutral. This pattern coincides with two internal processes referred to as the A process and B process. The A process, or affective response to a stimulus, is the initial emotional response one has and can be pleasant or unpleasant. The B process is the after-reaction and has a lower intensity than the A process. The A process is very fast-acting and ends as soon as the stimulus ends or is removed. Unlike the A process, B process is much slower in returning to baseline. Concerning the definition of the opponent process theory, repeated presentations present habituation. The A process does not necessarily change. It is the B process that is strengthened instead and rises more quickly to reach the highest intensity, and much slower in attempting to return to baseline after the stimulus is removed. To sum it all up with the opponent process theory, repeated presentations of the same stimulus will result in habituation. Where subjects show little to no reaction, it is the after-reaction that is much larger and prolonged than if an initial reaction to a stimulus occurred. Uses of the habituation procedure. Habituation procedures are used by researchers for many reasons. For example, in a study on aggression in female chimpanzees from a group known as the Kasakala chimpanzee community, researchers habituated the chimpanzees by repeatedly exposing them to the presence of human beings. Their efforts to habituate the chimpanzees before the field researchers studied the animal's behavior was necessary necessarily in order for them to eventually be able to note the natural behavior of the chimpanzees. Instead of simply noting chimpanzee behavior as a response to the presence of the researchers, in another study, Matumba chimpanzees in the Gombe National Park were habituated for at least 4 years before the introduction of systematic data collection. Researchers also use habituation and dishabituation procedures in the laboratory to study the perceptual and cognitive capabilities of human infants. The presentation of a visual stimulus to an infant elicits looking behavior that habituates with repeated presentations of the stimulus. When changes to the habituated stimulus are made, the looking behavior returns. A recent fMRI study revealed that the presentation of a dishabituating stimulus has an observable physical effect upon the brain. In one study, the mental spatial representations of infants were assessed using the phenomenon of dishabituation. Infants were presented repeatedly with an object in the same position on a table. Once the infants habituated to the object, either the object was spatially moved while the infant remained at the same place near the table, or the object was left in the same place but the infant was moved to the opposite side of the table. In both cases, the spatial relationship between the object and the infant had changed, but only in the former case did the object itself move. Would the infants know the difference? Or would they treat both cases as if the object itself moved? The results revealed a return of looking behavior when the object's position was changed, but not when the infant's position was changed. Dishabituation indicates that infants perceived a significant change in the stimulus. Therefore, the infants understood when the object itself moved and when it did not. Only when the object itself moved were they interested in it again. When the object remained in the same position as before, it was perceived as the same old boring thing. In general, habituation-dishabituation procedures help researchers determine the way infants perceive their environments. The habituation-dishabituation procedure is also used to discover the resolution of perceptual systems. For instance, by habituating someone to one stimulus, and then observing responses to similar ones, one can detect the smallest degree of difference that is detectable.